Welcome to the next class of Data Communication Networks. So today we are going to discuss a topic called multiple access. Basically the data link layer, which is the second layer of OSI model, is functionally categorized into two types of sublayers called data link control and multiple access resolution. In our previous classes, we were trying to understand about data link control, which includes two important functions called flow control and error control, along with framing and uh, framing functions. The second important function delivered by data link layer is referred as medium access control or multiple access resolution. So multiple access, also referred as medium access control, is a function performed by lower sublayer of data link layer. So if it is upper sublayer, it is referred as lower sublayer, and that particular function performed is referred as multiple access or medium access control. And what is the major importance of using this particular function? It tries to resolve the access of the shared medium. So we want to improve the efficiency of the channel. So how do we improve the efficiency of channel is to make more than one device to simultaneously use the channel. To implement that, what we are trying to do is we are trying to allow the channel to be accessed by more than one user. Now how and that particular channel is shared among multiple users is referred with a function called multiple access. So the lower sublayer of the data link layer which is performing it is referred as medium access control. To implement the multiple access or medium access control function, the data link layer is using a set of protocols which are referred as multiple access protocols. The protocols used to handle the access to the shared medium are categorized into three types. So the multiple access protocols are categorized into three types. What are them? Namely, random access protocol, control access protocol, and channelization protocol. So these three protocols are further classified into the following types. First, the random access protocol is further classified as Aloha, carrier sense multiple access, carrier sense multiple access with collision detection, carrier sense multiple access with collision avoidance. The controlled access protocol, which is the second type of multiple access protocol, is categorized into three types, namely reservation, polling, and token passing. The third type of multiple access protocol we are using is referred as channelization protocol, which is categorized as frequency division multiple access, time division multiple access, code division multiple access. We'll try to understand each of these protocols in detail in this class. The first type of multiple access protocols is called random access protocols. Now, what do we mean by a term called random access? In random access or contention methods, no station is superior to another station and none is assigned to control over the another. So all stations in your random access are equal. There is no one to dominate the others. So no station permits or does not permit another station to send. At each instance, a station has data to send, uses a procedure which is defined by its protocol to make a decision on whether to send or not to send the data. So here, every station is same and there is no station controlling the other station. So whenever they have some data to transmit, they use certain set of protocols and then they make a decision of whether to send or not to send. So the two important features of random access are there is no scheduled time for the transmission. Second, no rule specify which station should send the next. So random access protocols evolved from a protocol called Aloha. This is the first type of random access protocol which uses a simple procedure called multiple access. Now this particular Aloha, which is our first multiple access protocol, was improved with addition of a procedure called carrier sense, and that particular carrier sense mechanism will be referred as carrier sense multiple access. So first protocol is Aloha, which is a first multiple access protocol, and to that multiple access protocol we have actually added a mechanism called carrier sensing, and then we started referring it as carrier sense multiple access. So there are different methods of random access use. The first, as we mentioned, the first and most important type of random access is Aloha. So this earliest random access method was proposed in the year 1970s at the University of Hawaii. Aloha was designed for radio lengths, and there is a potential for collisions in that arrangement. So Aloha, which is the first random access protocol, is again categorized into two types called pure Aloha and slotted Aloha. Along with Aloha, its two types, we have three other random access protocols, namely carrier sense multiple access with collision detection, and carrier sense multiple access with collision avoidance. Now let us look at what is pure Aloha. So, and how frames are transmitted in pure Aloha network. So first, pure Aloha. In original Aloha, which is also called as pure Aloha, each station sends a frame whenever it has frame to send. So there is no particular schedule or any kind of uh, scenario required to send the frame. Whenever I have a frame to send, I'll be sending without looking for anything or for waiting for any kind of signal. So since all frames travel through the same channel, there is a possibility of collisions between the frames. In the figure, you could find totally station 1 sent 2 frames, 2 sent 2 frames, 3 sent 2 frames, and 4 have sent 2 frames. Totally, you could find 8 frames have been transmitted, but only 2 frames are reached successfully. What are that? Frame 3.2, this is success, and frame 1.1, and all remaining frames could not be succeeded. Now, so why only 2 out of 8 were success and why remaining failed are, in the remaining 6, even a small portion of one frame is colliding, or even one bit of frame of first frame is coinciding with the colliding with the other frames, you will find all the frames get damaged. So here 1.2 is colliding with 2.1, which is also colliding with 3.1, and 2.2 is colliding with 4.2, and you find all the 6 frames are lost. So 1.1 and 3.2 are only the frames which are not collided with any other frames. So hence they have reached successfully. And every time whenever there is a collision of the frames, we should not send the frames immediately because there will be further collision. So what we try to do is, once a collision occurs, we wait for a random amount of time before we resending the frame. So randomness helps in avoiding these collisions. Okay, this time is called backoff period. Let us look for the procedure of implementation for pure Aloha protocol. So we'll start our process. So the attempt number which we are making is referred with a variable k, and since it is our first attempt, we'll start with k equal to 0. So whenever a device has frame to send, it makes the first attempt k equals 0 and sends the frame. And once a frame is sent by a device, the pure Aloha, it waits for a total waiting time of 2 into TP, where TP refers to propagation time. So maximum propagation time is the time taken for a frame to travel from one end of network to the other end. So here we are waiting to time equal to twice the propagation time, and mean time, if we are able to receive the acknowledgement or not, is verified. If we receive a positive acknowledgement before twice the propagation time, then our transmission is success. But in case if we are not able to receive the acknowledgement even after 2 TP, then the acknowledgement received will be no. So we are going to make our second attempt. The first attempt was with k equal to 0. Now we are increasing our attempt number. So k equal to 0 plus 1, 1. So every time we need to make check out whether our attempt number is greater than or less than the maximum allowed attempts. Generally we set the maximum allowed attempt k max as 15. So 1 is less than 15, correct? So here the condition k is greater than k max. So 1 greater than 15 is false. So we'll go here. If the number of attempt is greater than the maximum attempt, there we have to abort our making retransmission attempt. But here since 1 is less than 15, next we are going to choose a random number r. The random number r will be chosen with 0 to 2 power k minus 1. Here k equal to 1. So 0 between r will be 0 and 1. And accordingly, we'll wait for a time called TB. So the value of TB is r into TP or r into TFR, where TFR refers to the average frame transmission time. So after this particular wait time is completed, we'll again send the frame. Again the process repeats. Once we send the frame, wait for 2 TP. If we receive an acknowledgement, okay. Else increase the attempt number. If the attempt is less than maximum attempt, then wait for a certain time TB and then retransmit the same frame. If the attempt number is greater than 15, then abort your transmission. So this is how the pure Aloha protocol is implemented. Now, in pure Aloha protocol, the time where there is a possibility of having a collision, we are referring with a terminology called vulnerable time. Vulnerable time is the time in which there is a possibility of collision of a frame. Generally, if you talk about a frame A, so the could find the another frames B and C can collide this particular T2, T, T plus TFR. So this is the total frame transmission time. So here you have T minus TFR to T plus TFR. So total time where there is a possibility of having a collision is from T plus TFR to T minus TFR. So this total duration is the time where there is a possibility of collision, and that is called vulnerable time of pure Aloha, which is equal to twice the frame transmission. Well, so far we tried to understand what do we mean by pure Aloha, then what is the procedure followed for pure Aloha, and we talked about the vulnerable time of pure Aloha. Now, last thing we need to know about pure Aloha is what is the throughput of pure Aloha. But before that, what do we mean by a term called throughput? A throughput is defined as a ratio of number of successful frames transmitted to the total number of frames transmitted. Let us refer back to our previous example where you tried to send 8 frames in which only 2 frames were successful. So what is the throughput in this case? Number of successful frames are 2 divided by total transmitted frames are 8. So throughput in that case was 2 by 8, which is equal to 1 by 4, which is equal to 0.25. So, but if you are making an assumption that we are sending G average number of frames during a frame transmission time TFR, then the throughput of pure Aloha is given with an expression capital S equal to G into e power minus 2G, where G is the number of frames transmitted during a frame transmission time and S refers to the throughput. The maximum throughput for a pure Aloha occurs when your maximum number of frames transmitted during transmission time is G equal to 1 by 2. So for every TFR, if you are sending half frame, so for a 1 TFR, if you are only sending half frame, then we are going to have the maximum throughput for pure Aloha, which is 0.184. To get this particular expression, what we have to do is we have to take this equation, then differentiate your throughput equation with respect to average number of frames G and make this value equal to 0. So when you do this expression, what we happens is we will able to get the value as G equal to 1 by 2. So once you get G equal to 1 by 2, substitute G equal to 1 by 2 here. What happens is G 1 by 2 into e power minus 2 into 1 by 2. So we are going to get half into e power minus 1 finally, which is going to be equal to 0.184. So this is how we are actually deriving the expression for throughput of pure Aloha. At the same time, what is the maximum throughput of pure Aloha? The next type of Aloha protocol which we are going to discuss is called as slotted Aloha. So let us look at what do you mean by slotted Aloha and how frames are transmitted in the slotted Aloha network. So what is the drawback that we could identify in pure Aloha is any device can send any frame at any instant of time. Because of it, you could find more collisions happening in pure Aloha. To overcome that drawback, we are trying to implement the next protocol called slotted Aloha. So term slotted. So what it means is, in slotted aloha, we are going to divide the total time into smaller units called slots. In slotted aloha, time is divided into slots and each station has to send frames only at the beginning of new time slot. We cannot send whenever the data is available. So we have to either send at the beginning of a time slot. That time slot we are not ready, we have to wait for the next time slot. For instance, you are being allowed to the class before the faculty comes. In case if you are not entered by that time, so what is as per norms you have to do? You need not enter the class into the middle because you are going to disturb entire class. Instead of that, you can come to the class in the next hour. So you can send a frame at the beginning of a time slot, else you have to wait until the next time slot. So any device can send frames. So any device can send at the beginning of a time slot, else it has to wait for the next time slot. So since we are having only this facility of sending the frames at the beginning of the slots, we call this type of protocol as slotted aloha. So in slotted aloha, the time is divided into slots and each station has to frames only frames at the beginning of the time slot. If station misses to send the frame at its slot, it has to wait until the beginning of the next slot. So what happens here is, when compared to pure aloha, the collisions are reduced because we cannot send at any instant of time. So marginal collisions is not happening. So if collisions are occurring, yes, but that collisions will be, the entire frames will be colliding with each other. So here 2.1, which is the frame sent by station 2, and frame 3.1 sent by station 3, both are colliding together. At the same time, frame 1.2 of station 1 and frame 4.1 of station 4 are colliding. So these 4 frames are collided, so they cannot be transmitted. Remaining 4 frames are not colliding with any other frame. So here, out of 8 frames totally transmitted, 4 are successful. So 4 out of 8. So here the throughput is 50% compared to 25% in pure aloha. So the throughput of slotted aloha is given by an expression throughput S equal to G into e power minus G, where G is total number of frames sent during the frame transmission time TFR. When you implement the ds by dg and try to equate it to 0, here what happens is you will get a value of G equal to, so take the derivative of throughput ds with respect to dg and try to make it as 0. So here you will get the value of g as 1, and when you substitute 1 here, 1 into e power minus 1, so you will get a maximum throughput of 0.368, whereas the throughput maximum in case of slotted aloha, pure aloha is 0.184. The throughput in case of slotted aloha is 0.368. I hope this is clear. What is the vulnerable time for slotted aloha? So we mentioned that vulnerable time is the time period in which there is a probability of collision of one frame with other. Since in slotted aloha we transmit frames only at the beginning of a new time slots, so here we will have a collision only during the frame transmission time. So vulnerable time of slotted aloha is only TFR, which is the frame transmission time, which is half of the vulnerable time of pure slotted aloha, which is 2 times the frame transmission time. Right. The next type of random access protocol is called as carrier sense multiple access, which is a modified version of pure aloha. In pure aloha, we were transmitting the data whenever we have, or we are waiting for the time slot and trying to send the data. But in both the cases, we are not trying to find out if the channel which we want to use to send the data is available or not. So that particular function of sensing a channel before transmitting, we call it as carrier sense, and it is used to transmit multiple devices on the same channel. So it is called carrier and sense multiple access, in short CSMA. CSMA is a multiple access technique used to minimize the collision and maximize the efficiency as it senses the medium before trying to use the medium. It's simple like before you enter on a road from your home on a bike, what you try to do first near your gate, you try to look at both the directions. Does any vehicle is passing on the road? When you are clear that no vehicle is passing on the road near to you, then only you try to enter the vehicle. Here also when you are trying to send the data, you are trying to ensure whether that particular channel is free or not, then only you are trying to use that channel. So that is why carrier sense multiple access is also referred as sense before transmit. In CSMA, there is still collision because of propagation delay. So basically when you try to sense a channel, might be the channel was free, but there might be some other device which have already sent the data in the past that might be traveling with a later time, and you could find at some time these two frames will be collided and we will have a collision. Maybe the time at which you try to sense the channel was free, but there was someone behind who was actually transmitting the data, and some point of time you will find a collision. Let us look at this. Here the device, we have totally four devices A, B, C, T, and here the device B started transmitting data at time t1. So here it is sending in both directions. So B's transmission started at time t1. At time t2, C tried to sense the channel. By the time it was sensing the channel, the B data was not reached here. So C felt that there is no one who is actually using the channel. So what happened at time t2, when it sensed no other device was identified, so it started transmitting. After both the devices B and C now started transmitting, at a certain time you could find both the data has been collided. So here blue exclusively for C, yellow exclusively for B, and this portion you could find both the devices data are mixed, which means there is a collision. We try to minimize the collisions, but still collisions are possible in the carrier sense multiple access because of the factor called propagation delay. Vulnerable time, which actually indicates the probable time of collision in case of CSMA. So vulnerable period for CSMA is the propagation time, which is the time taken for a signal to propagate from one end to other. For instance, you talk about the station A. So whenever a station A has data to be sent to station D. Now in the meantime, there is any chance that B senses a channel here found idle, transmits and get collided with A. C senses at a time, maybe at that time there is no collision, but later might have a collision, and D here. So you could find, so at any instant of time, there is a possibility of having a collision for frame device A, which sends its frame. So the maximum vulnerable time for a device in carrier sense multiple access is equal to the propagation time, which is the time it takes for transmitting from one end to the another. To implement carrier sense multiple access, we are using certain persistence methods. So persistence methods, they are used to understand what a station must do if a channel is busy or if a channel is idle. So basically we have three persistent methods. So it actually tries to tell what should we do if a channel is busy or what should we do if a channel is idle. So persistent methods are categorized into three types. What are that? Single persistent, non-persistent and p-persistent. Let us first look at single persistent. In single persistent CSMA, a station continuously senses the channel. If it finds a channel idle, it immediately sends the frame with a probability of 1. It has a high probability of collision. So what it means? Here you look at the station continuously sensing the channel, and immediately at some time it found a channel is idle, and immediately it will transmit. So once you sense a channel idle, you transmit with a probability of 1. You refer it as single persistent channel. Now second type of persistent CSMA is called non-persistent CSMA. What do we do here is a small different from what we found in single persistence. In single persistence, we are continuously sensing a channel until we find the channel as idle. But here, we sense a channel and finds it busy, we wait for some time before sensing a channel idle. If it finds a channel idle, it immediately sends the frame. So here also if a channel is found idle, it will immediately sense the frame. And this method reduces the probability of collision. How it is reducing the probability of collision? When you find a particular channel as busy, instead of continuously sensing it, we wait for some time before we sense once again the channel. Here also you found channel busy, you waited, sensed the channel, again it was found busy, you waited for some time, and later once it sensed, it was found free, immediately you transmit. That is called non-persistent carrier sense multiple access. The third method of persistent method is called p-persistent method. Here actually it is trying to combine the effects of single persistent and non-persistent. In this method, you will try to send a frame. The probability is p, and you will be trying to avoid sending of the frame. The possibility is q equal to 1 minus p. So as we mentioned, we are combining the features of one persistent and non-persistent. First, as a feature of single persistent, you find here continuously sensing the channel, and you try to continuously sense the channel until you find the channel as idle. But here what happens is you will try to find out the probability outcome. If the probability outcome is p, then you try to transmit. The probability of outcome is 1 minus p. You try to wait for the next time slot. That is how they are trying to implement in case of p persistence. Here depending on the probability, you will be either deciding to send the frame or wait until the next one. For instance, if the probability is good, which is accepted, if probability is less than p, you will send. Probability is greater than p, which is q equal to 1 minus p. Then you wait for the next time slot. Again you check the probability. If it is greater, then you wait. When it is lesser than p, you will be trying to transmit. Let us look at the flowchart of the three persistent methods. The single persistent, what did we discuss is, we are continuously sensing a channel, and whenever a channel is busy, we are again sensing it until we find the channel is idle, and once the channel is found idle, we are transmitting with a probability of 1. Whereas in case of non-persistence, we will not continuously sense the channel. First we will sense a channel. If it is idle, we transmit with probability of 1. But in case if the channel is found busy, we are going to wait for a random amount of time before we once again sense the channel. This is the non-persistent method. And combining the features of single persistent and non-persistent, we have p-persistent method, where we first sense the channel. This channel is found busy, we continuously sense it until we found the channel as idle. Once the channel is found idle, what do we try to do next? So once we try to find a channel as idle, we are trying to determine the probability of outcome. Here, the probability of outcome is less than or equal to p. We are trying to transmit the data. If the probability outcome is greater than p, we are going to wait for a slot and then again sense the channel. If it is idle, then we will again check for the probability outcome, and only when the probability is less than or equal to p, where p is the probability of collision, then only we are trying to transmit. If the probability of collision is greater than p, we definitely wait for a slot. This is called p-persistent method. Carrier sense multiple access technique, which we discussed in the previous session, we were talking only about sensing the channel before using it, and for that we are using different persistent methods. The next type of carrier sense multiple access technique is called carrier sense multiple access with collision detection. So what do you mean by collision detection and how it makes it better than the CSMA? Let us look at it. So in CSMA, what we are trying to do is we are sensing a channel till it is free, and once it is free we are trying to transmit the data. But once we are sending it, we are not looking care whether that data has reached a destination successfully or not. So here in CSMA CD, we try to implement an algorithm to handle the collision, which is not happened in carrier sense multiple access. In this method, the station monitors the medium after it sends a frame to see if the collision or the transmission is successful. The station monitors till the last end of the last bit. If the transmission is successful, it removes the frame. Else, transmission is unsuccessful, it could find some collision, it will retransmit the entire frame. So minimum frame time for carrier sense multiple access collision division is twice the propagation time. In case a station identifies or detects a collision, it immediately aborts its transmission. So what exactly a carrier sense multiple access collision detection is? Not only sensing whether the channel is free or not, but after sending the data, it will be monitoring whether the data is transmitted without any collision or not. In case if you find any collision, you are going to retransmit the frame. If once the frame is observed that entire all data is transmitted without collision, we will be removing that frame. So whenever you identify a collision in the transmission, you have to immediately abort the transmission. Let us try to understand this concept using this particular figure. We have four devices A, B, C, D, and here the device A starts transmission at a time T1. It sends the channel, it finds it idle, so it starts transmitting. At time T2, the C sends the channel, but at that time, since A's data has not reached to C, it finds the channel as idle. So C also starts transmitting at time T2. Now what happens? A is transmitting through same channel, C is transmitting through same channel. At a time T3, both the data will be collided. And once the two data are devices are collided, what happens? Whenever C identifies that there is a collision, it immediately aborts. We just said that whenever a collision is detected, it will start transmitting. But A is not aware about the collision till the time T4. At time T4, it can understand there is a collision in the transmission, and immediately after identifying it, it aborts the transmission. So A started at T1 and transmitted till T4. So the transmission time of A is T1 to T4, whereas T2 is the time at which C has transmitted, and it was transmitted till T3, where a detection is identified and it aborted the transmission. So this is how a carrier sense multiple access with collision detection is happening. What is the additional feature you can find here is, after a frame has been transmitted, the station monitors if there is any collision or not. In case if a collision is identified, abort the transmission and try to retransmit the entire frame. So this is how your carrier sense multiple access with collision detection is different from carrier sense multiple access. And here the minimum frame time which is used is twice the propagation time. Now let us look at the flowchart of implementation of carrier sense multiple access with collision detection. So we'll start our transmission. Our first initial attempt is k equal to 0, and we are trying to apply one of the three persistent methods which we discussed. Namely, what are that? Single persistent, non-persistent, or p-persistent. And by applying one of the techniques, we are trying to sense the channel, and once the channel is free, we are implementing the transmission. Now once the transmission is done, we are continuously monitoring if any collision is detected or not. If collision transmission done is collision detected is no. So transmit and receive, and here when no collision is detected, it means that our transmission is successful. So transmission done and collision detected is no, your data transmission is success. But a transmission done, but if a collision is detected, you have to retransmit the same frame. Okay, so your transmission is done and collision detected. So what happens whenever you find a collision during the transmission? We'll send a jam signal saying that a collision has happened, and now we increase our attempt number as k equal to k plus 1, and we will verify whether our attempt number is greater than or less than the maximum attempt number 15. If it is less than 15, we will be continuing the process. If it is greater than 15, we abort the transmission. So when it is less than 15, we'll try to choose a random number between 0 to 2 power k minus 1. Here k equal to 1 for the next attempt. Later it becomes 2, 3, and so on. So once we determine the value of r, we'll try to make a waiting time. Waiting time is equal to r into tp or r into tfr. And after this wait time, again we try to sense the channel using one of these three persistent methods. So here what we are trying to do is we are trying to transfer the data, and we are finding out if any collision is detected or not. If collision is detected, we are aborting, we are sending a jamming signal and trying to retransmit. If no collision is detected, we are successful in transmitting the data. Now, the throughput of carrier sense multiple access with collision detection, where you are trying to not only sense the channel but also trying to look at if there is any collision or not. So what happens is its throughput will be greater than pure aloha and slotted aloha. And the maximum value of throughput for CSMA CD is based on the persistent method which we are using and also the value of P which we are using for P persistence. For a single persistence, the maximum throughput is 50%, and for non-persistence, the maximum persistent depends on the value of G between G equal to 3 to 8. How do we try to understand whether a collision has occurred or not? For instance, when a device has not set any frame, that is, it is in idle state, the energy level in that idle state will be 0. But whenever it has only set one frame, it will be having an energy level greater than idle state. But what happens when the collision happens with some other device frame is you'll find an abrupt increase in the energy levels of the frames. So this will try to indicate that there is a collision of our frame with other frame, and hence we have to abort the transmission. So when energy level is 0, you are idle. When energy level is normal, there is no collision. But whenever the energy level is very high than the normal level, it indicates there is a presence of collision. The last type of random access protocol, which is another version of carrier sense multiple access, is called as carrier sense multiple access with collision avoidance. This is particularly used in the wireless networks because in wireless networks the collisions cannot be detected as in the case of wired network. Now, to handle the collisions in wireless networks, what we are trying to do is we are implementing carrier sense multiple access collision avoidance, and for this three strategies are being adapted. What are that? The first one is called interframe space, the second one is called contention window, and the third one is called acknowledgement. Now what do you mean by interframe space? Now here, as discussed in single persistence, here also you are continuously sensing a channel and it is busy, and you are doing it until you find the channel to be idle. So, to avoid the collision which may have happened in wired networks, what we try to do here is, even though once you find a channel to be idle, you are waiting for a particular duration called IFS, which is interframe space. So to avoid collisions, we defer a transmission even if channel is found idle. When the idle channel is found, it waits for a period called interframe space. This is the first level of strategy you are trying to use to avoid the collisions in wireless networks. Then the second strategy which we are adapting is called the contention window. So what is this contention window? Here the time is divided into slots and station selects a random slot as its wait time. The number of slot changes according to binary exponential backoff strategy. Now what it means is, after interframe space, first time I will wait for a one time slot and then again check if the channel is free or not. If channel is free, then I can send the frame. If channel is not free, then I have to increase my exponential wait time. I need to wait for 2 slots. Next time I need to wait for 4 slots, then verify it. But whenever I could find a channel free after this particular contention window, then I'm trying to send the frame, and after sending a frame, whether that frame has received successfully or not, what I'm trying to do is I'm using my third strategy called acknowledgement, where I expect a positive acknowledgement from the receiver before the timer expires, and this positive acknowledgement can guarantee that the receiver has received the data. So in carrier sense multiple access collision avoidance, we are trying to ensure the collisions are avoided by using three strategies, namely interframe space, then using a contention window, increasing the binary exponential backoff strategy, and then using a positive acknowledgement. So this is how we are trying to avoid the collisions in wireless networks. So far we tried to discuss about what do you mean by multiple access, where more than one device would try to transmit the channel. So to avoid collisions in wireless networks, we are trying the carrier sense multiple access with collision avoidance, which is using three strategies: IFS, contention window, and acknowledgements. In carrier sense multiple access with collision avoidance, the interframe space which we are using, even though when the channel is idle, waiting for certain time, it can be used to define the priority of a station or a frame. In carrier sense multiple access collision avoidance, if a station finds a channel busy, it does not restart the timer of contention window. It stops the timer and it restarts it when the channel becomes idle. So whenever the station has found something, the channel busy, so it will be stopping the timer and it will restart the timer only when the channel becomes idle. Just few points need to be remembered. Now let us look at the flow diagram of carrier sense multiple access collision avoidance. So let us look at what are the changes which we have compared with CSMA and CSMA-SIG. Here, first we'll start our transmission attempt. So k equal to 0. Now we are trying to sense till the channel is idle. If idle channel is no, we're continuously sensing until we are trying to find the channel is idle. Once you find a channel idle, here as we discussed, first we'll try to wait for a time period called interframe space. So wait for an interframe space. Even after wait interframe space, the channel is idle, we move further. After interframe space, if it is not idle, we go back and repeat the process of continuously sensing the channel and trying to find if the channel is free or not. After finding a channel idle, we are waiting for interframe space. Suppose after interframe space also the channel is found idle. Then we are trying to make a random number r between the choice 0 to 2 power k minus 1. K is our attempt number. Correct? So after this, we are trying to determine a wait period by multiplying or the way of waiting for a wait r number of slots. And once the wait period is complete, we are trying to send the frame and we are waiting to receive a positive acknowledgement before the timer. If we are able to receive the acknowledgement before that timer reaches 0, it means our transmission is success. But in case if we don't get a positive acknowledgement before the timer expires, it makes our transmission is not success. So we increase our attempt number from k equal to 0 to k equal to 0 plus 1 and verify whether the attempt number is greater than 15 or not. If it is less than 15, we can go for the next attempt. If it is greater than 15, we have to abort the transmission. So if it is less than 15, go back, sense the channel. If a channel is found idle, wait for the interframe space. After that also it is idle, select one of the random slots and then send the frame. After sending the frame, if you receive an acknowledgement, transmission is successful. If no acknowledgement is not received, go for one more attempt till it reaches 15. And once it is making a attempt number 15, you have to abort the transmission. So this is all we have discussed about different types of random access protocols. A random access protocol is something where every station is having same powers or same kind. There is no one to control the other, and different stations will use different protocols to decide when to transmit the data. The first of this random access protocol is called Aloha, which is categorized into two types: pure Aloha and slotted Aloha. In pure Aloha, whenever you have a data, you can transmit, because of which you have higher collisions. The modified version of Aloha is slotted Aloha, where you can only transmit the frames at the beginning of a new time slot. And coming to the next is carrier sense multiple access, where you try to improve the throughput and reduce the collisions by sensing the channel before transmitting. There, because of the propagation delay, you could find some collisions. To overcome that, we are adapting the next protocol called carrier sense multiple access with collision detection. That is only applicable for wired networks, where you have, even after sensing the channel and transmitting, you will wait until all the bits of the frame must be transmitted. If any collision is detected, immediately you have to abort. But this particular algorithm is only suitable for wired networks, which we cannot implement for wireless, for which we are implementing carrier sense multiplexers with collision avoidance, where you are making three strategies. One is, if finding a channel idle, we are waiting for a time called interframe space, and even after that, if channel is idle, we are making some random slots and determining one of the slots and then transmitting the frame, and after sending the frame, setting a timer and expecting a positive acknowledgement. In any of these three stages, if we fail, we go for reattempting by again sensing the channel and repeating the process. So this is all about what do you mean by multiple access and different random access protocols. Now next class we will be talking about the controlled access and channelization protocols. Along with this, we will also try to discuss the IEEE 802.11 MAC protocol. Hope you people have gone through this class. Make sure you refer all this content and go through the flowcharts, because this is one of the very important topics for the examination. Meet you in the next class.